we said that ionization is removing an electron. So we have to put in energy in order to do that. So the energy that is required to remove an electron is called ionization energy. I wrote an example here that shows you what an equation looks like for the removal of an electron. We start with the neutral atom, and then over here on the product side, we see that we end up with one electron being removed and the ion that results after the removal of the electron. So you can remove one electron or you can remove more than one electron. So removal of the first electron is known as the first ionization energy. Mm-hmm. This right here? Yes, that's one electron. Is it fuzzy up there? Do I need to tweak that? Okay. Okay. Can everybody see in the back? Okay. All right. If we go in and we remove a second electron, then it's going to require even more energy. So this will be the first ionization, and this will be the second ionization. So over here, if you see what the energy is for each one, the energy that was required to remove that first electron is 496 kilojoules per mole. But if you look at how much is required to remove that second one, it requires a whole lot more energy to remove each successive electron. And that's because as you remove the electrons, the remainder of the electrons have such a attraction for the nucleus that they are not going to want to be removed. Okay, so your next slide actually has a summary of this. Is everybody done writing on this page? Okay, thanks. Mm-hmm. The second ionization starts with the ion that we produced with the first ionization, which is the sodium ion in the plus one. The plus sign is the ion. That tells you that it is a cation in the positive one cation. So when you remove the electron, remember we form cations. Okay, removing an electron from a neutral atom um, forms a cation. Adding an electron forms an anion. So what this equation here is showing us is that we have removed an electron. This is the electron we removed, and this is the cation that we formed. That was the first ionization. When we go down to the second ionization, that means that we already have removed one electron right here. So the second ionization means that we're going to remove a second electron, and it's going to have not a positive one, but it's going to have a positive 2 charge because we've removed another electron and we've reduced the positive charge by 1. Increase the positive charge by 1. Okay? All right. So there's a slide here that summarizes all of that. It tells us the minimum energy required to remove an electron from an atom or an ion. We have to put energy in, which is what I just said, which means it's an endothermic process. The valence electrons are the easiest to remove because they're swimming on the outside of the atom. But as you get past the valence electrons and start going toward the core, toward the nucleus, where those electrons are more tightly held, then the ionization energy gets much higher because it's much more difficult to remove those electrons, right? So basically, this is another example right here of two of the successive ionization energies, the first one and the second one, for um, this just is a generic metal. I'm like, we don't have an element name for them. Okay. Right. And if you move two electrons, you're going to get a positive two charge. And this is the equations that we see. This is the first one. This is the second one. IE means ionization energy of the first ionization energy, and the second ionization energy. And that's important because that's how it's going to be written when you see your problems and probably on your test as well. Yeah, you'll probably see where you're going to be asked to write the equations for both of them, where it tells you to um, show writing ionization energy for the first and second ionizations. And actually, it's one of those in your practice problems that you have. Mm-hmm. Okay. So you got in the and so, you know, when you have a neutral atom, which means it's in its ground state. No, electrons are negatively charged, right? So every time you remove one, you end up reducing that net negative charge. So if you reduce the negative charge, you're going to end up creating a positive charge. So for every electron you remove, you're going to create a positive charge of 1 unit. So if you remove two electrons, that's removal of two negative units, then you're going to end up having a positive 2 ion there. And the ionization energy, the first one here, tells us how much energy we have to put in order to make that +1 atom and remove the electron. That's the first ionization energy. Here, IE2 is the second ionization energy. That's the energy required to remove the next electron. Right. Because you have some atoms that go up to the third and fourth ionization energy. So IE is the ionization energy, and whatever the subscript is here tells you that's the number of the ionization. Right. Exactly. Okay. All right. So now that we kind of got an idea of what this is, let's look at the trend in ionization energy. Okay. The trend in ionization energy is that as we go up a group and across, it gets bigger. So, same thing as it says here. It decreases down the group and increases across the period. So, the largest ionization energies are toward the top and over to the right. Why is that? Your next few pages have notes. Yes. But I would love to have I'll be happy to get that done. I've been worried about that. Okay, so the next few slides have notes that tell you why, but remember, we always go back to the effective nuclear charge to explain these things. So as you get, uh-huh, mm-hmm, It does. So I have the up arrow to mean it gets bigger in these directions. So it gets bigger up the column. So it decreases. This is a smaller end. This is a smaller end. I'll draw a little dot down here. And then it gets bigger as you go that way. Well, to the right. The reason is it's largest up here because there's less as you go, it's largest as you go toward the top of a group because you have less energy shells. So therefore, um, the electrons are drawn more closely toward the nucleus and they're more difficult to pull away from the nucleus. The same is true as you go across the period. Remember, the effective nuclear charge gets greater as you go across. So therefore, the electrons are held more tightly as you go from left to right. So therefore, it is much more difficult to remove an electron over as you go up and as you go over. So that's the trend in ionization energies. So ionization energies get larger as you go up and larger as you go from left to right. So I'm going to peek at the next slide right quick and see what I have here. I'm not going to explain that like I tried to last time, but this is just a graphic that that summarizes that relationship. It's larger toward the top and toward the right hand side. So let's look at a couple of different examples. And I want you to tell me what's bigger. I'm going to look at the next slide right quick. Okay, yeah. So this is just the explanations down here as to why. Okay, these are the explanations. So I always wish I put a periodic table in here. But looking at that periodic table on the wall, tell me which is bigger. Okay. Or sulfur. I'm going to write all these down so as we go through, we can work them all out. All right. And these examples are on page 361 of your book. So this is our relationship, our trend. Okay. So looking at the periodic table, which is bigger, aluminum or sulfur? So is to the left of sulfur. So it gets bigger as you go this way, right? So sulfur is the biggest. Arsenic or antimony, they're in the same family. So they're in family 5. Mm-hmm. So this is arsenic, this is antimony. So the trend tells us that we get larger as we go up, right? So which one is biggest? Okay. And the same is for, let's see if I can draw this. Nickel, I'm sorry, nitrogen and silicon. Okay. I keep wanting to make this nickel for some reason. Nitrogen. All right. Nitrogen is bigger. What about the last case? Remember, the last one is usually something that, yeah, you can't really tell because you go bigger as you get in this direction, but then you also go smaller. So it's kind of an offset. So they kind of cancel each other out, so you cannot tell. All right. So that is how we can predict trends in ionization energy. So that was removing an electron. What about putting an electron on, acquiring or gaining an electron? That's next. These are some exceptions that you can memorize. When you go from 2A to 3A and from 5A to 6A, the energy offsets each other. So in your notes when you're studying at home, look at these two slides and make note of these two exceptions and the explanation as to why. All right. So this slide, before we leave ionization energy, all this shows us is that as you see going from blue to purple, that's going from removing the last valence electron to starting to mess around with the core electrons. And as you can see, in each case, that ionization energy increases a lot because the core electrons are tightly held to the nucleus. They do not want to be removed, and there is a lot of energy that is required that has to be put in order to pluck an electron out of the core. So keep that in mind. They're experimentally determined. Mm-mm. You just need to know that the ionization energy increases a whole lot when you start trying to pull out core electrons. Okay? All right. So, just like we had ionization energy, removal of an electron, now you've got electron affinity, gaining of an electron. So the electron was on the product side, right? Which means we removed it and it came off and it was left as a product. This time we're putting it in as a reactant. So we're putting it in on the left side. And when we do that, when we add an electron to something, we increase the units of negative charge, right? So negative charge um, for every electron gained. It didn't go in, your book didn't go into specifics about gaining more than one electron, um, and we don't really have any successive electron affinity, but so therefore, for electron affinity, you just need to know what the first electron affinity is. So just know that adding an electron to any atom increases its amount of negative charge by 1. So when this happens, we had to put energy in to take the electron off, to ionize the electron. But when we put an electron on, gain an electron, we get energy out. It's an endothermic process. So this is the same thing as that. And this EA here is what we call the the electron affinity. Wrong class. Okay. So the trends for this one are not as predictable. And I'm going to try to summarize this with a graphic here. The alkali metals, which is group 1A, we can pretty much anticipate that the electron affinity gets bigger as we go toward the top of that column. As you go across a period, the electron affinity also increases. The halogens over here are the most electronegative. They really, 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 when you go across a period, the halogen is the most electronegative because, remember, electronegative and it has the highest electron affinity. I'm speaking from another class now. I've probably taken, have you gotten into electronegativity in your last class? No? Okay, so it has the highest electron affinity because it's the closest supernova gas. It already has 7 -7, and it wants an electron so bad, the halogens do. So therefore, the halogens have the highest electron affinity because they want to look like a noble gas so, so, so bad. So therefore, you can predict that they have the highest electron affinity when you go from um, left to right within a period. Okay, um, but other than that, you can't really predict. So generally, when you go from left to right in a period, and always when you go from bottom to top in the first period, which is the alkali metals, you increase the electron affinity. But all this other, when you go up or down the column, within the other columns, you can't generally predict. Okay, so let me reiterate that. You can generally say that going from left to right increases electron affinity. You can say that going from bottom to top in the first column increases the electron affinity. But it's difficult to say going from bottom to top in the other columns what happens with electron affinity. So let's look at a couple of examples. And this is just a summary of that. See the halogens, they kind of follow that same trend for the most part. You can see as you go over, they pretty much get more electronegative as you go. The halogens are the most electronegative in the whole period. It's all of this is, you really can't tell. Okay, so let's look at a couple of examples. I had made you some examples. Let me give you my examples and see what we can figure out. Let's look at the periodic table. I'm going to go back to the previous slide and give you some examples that you can write down here. Which is bigger? Well, which has the highest electron affinity? Um, Sodium or potassium? Why would you say sodium? And it's in group 1, so you can pretty much predict, right? What about potassium or krypton? Krypton is way over there to the right. Actually, that's a bad example. Let me give you a different one. Okay, potassium or bromine? Remember, we're going across, so we can pretty much speculate. We say that since bromine is a halogen, it pretty much has the highest electron affinity in its period, right? So that's how you can tell kind of electron affinities. And what about going from manganese to uranium, Re? You really can't tell, can you? Unless you have a table in front of you that gives you specific numbers, you can't tell by trends alone because they don't fall within one of the predictable zones on the periodic table for electron affinity. All right. Okay. So the last thing that we're going to cover in the chapter is metallic character. How close to looking like a metal or having properties similar to a metal that something is. Metals have very, very specific properties. They're malleable, which means that you can easily take a hammer and beat them into a shape. Shiny, lustrous, reflect light. all of these are properties of metals. On the other hand, your nonmetals are more brittle, they're dull, they don't reflect light, they're kind of boring in terms of, yeah. But we can predict a trend based on the periodic table that tells us how close to looking like a metal that something is. So we already know basically where the metals lie on the periodic table, right? We pretty much know that the metals all lie to the left side, right? So the metal character increases as you go from right to left on the periodic table. The metallic character, which is what we are describing in this trend, the metallic character increases as you go from right to left. And it increases as you go from top to bottom in a column. So the element that has the highest metallic character, uh-oh, is francium. I think it's at the bottom down here. Thought I had a slide on that. Okay, so basically that's how you predict your trend in metallic character. Which one exhibits the most metallic character? So some examples of those. I can't tell if this is tin. Okay. All right. So based on their location on the periodic table, tin and beryllium are in the same row, right? So we get bigger as we go from this direction to this direction. So tin is the largest. Germanium and indium, we get bigger as we go this way and as we go this way. So indium is the obvious choice, right? Uh-oh. Sulfur or bromine. This is not a negative charge here. Let's see where they are relative to one another. And of course, we get bigger as we go this way and as we go this way. So they cancel each other out once again. Uh-oh. If you go this way. Okay. So that's metallic character. So that ends the content that we're covering for this chapter. So what I want to do is take one of those, any blank space that you have, or take a new sheet of paper, and I'm going to do a review for you, which basically is a recap of everything that we've learned and should remember in this chapter, in its most basic and compact term. We're doing the whole chapter. Start from the very beginning. What should you know? Number for an electron in a specific orbital. You know how to write electron configuration? And how to draw orbital diagrams. Okay. We know that we have rules that are associated with this, and that they have a certain order of filling. And remember, we could make our own little order of filling chart, blah, 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 and then draw your arrows and get the right order, right? We know that we only can have 2 electrons at a time in an orbital. We know that we fill one at a time with parallel spins before we pair them up. Okay, so all of that is basic information for electron configuration and for orbital diagrams. We know that the order that we fill them in is dictated by our little chart. We know that we can denote a noble gas shorthand configuration using the previously filled, completely filled noble gas. From these things, we can identify core electrons and valence electrons. And then once we know what the core and valence electrons are, we can also write this for cations and anions. We know that anions add an electron. Cations remove electron. So when adding an electron, we do it in the orbital that the electrons fill here. But when removing an electron to form a cation, remember we remove from valence. Can we or didn't? So let's say we've got the titanium. Okay. Titanium, in order to add an electron to that, we would put it in the 3D, right? So we would go to 3D3. We do it in the same order that we always fill our electrons in. Okay. To the right. 4 is the outer shell. So 4 is our actual valence shell. So to remove an electron, we have to come out of the highest energy, the highest principal quantum number value, which is the 4. Okay, so that's our actual valence. To add it, you do it in the same order that you do using this little chart. Okay. Remove it, you always take it from the valence. And the valence is the one that has the highest N value. So the highest principal quantum number. Exactly. And I did put a lot of examples of all of this. Everything I'm talking about in this review, I have a sheet here. I have some practice problems for you to take and try to apply this. And I'm going to put solutions to these on YouTube. So you can, I have a YouTube channel where I put the recorded lectures. I put any tutorials that I do for you. So I will solve these problems. If you have any questions, any problems or difficulties, you can look at it on your phone. No reason you can't access it. So it'll be on Blackboard. Okay. So the link to it is always on Blackboard. So same for these lectures in class, provided that they continue to record successfully. You can go back and listen to the lecture, and the solutions to these will be on there as well. So I'll do that. I'm probably going to wait till tomorrow to do it to give you a chance to try to apply some of this yourself. Okay, so the next thing that we did that you need to do remember how to do all this stuff. This is something that we need to remember how to do it. And so we saw the trend in effective nuclear charge, and that's in your notes as well. But we use effective nuclear charge now to be able to predict these trends using a periodic table. And these trends, remember, were for the arrow is going to be in the direction that the property gets largest. So atomic radius is largest in these directions. Remember, for atomic radius, we were able to compare cations and anions. So the atomic radius for both the neutral atom as well as the cation and the anion go in this general trend. But remember, for cations, they're smaller than their neutral atom. And the anion, because the cations are smaller because you remove the electron cloud, you remove electrons. And so therefore, the size is smaller, and then the Z effective allows you to pull it in tighter. So anions, on the other hand, are larger than neutral because you've added extra electrons on the outside. So for atomic radius, that's the direction it goes in. Always remember, cations are smaller than the neutral atom, Anions are larger than the neutral atom. Ionization energy, which is IE, we saw that it follows this trend, and we said there are exceptions, except 2A to 3A and 5A to 6A. Electron affinity, which is EA, we said we can definitely predict it in the first column there for the alkali metal. We know that generally it gets bigger across a period. But we said all of this in here is a fuzzy bubble. We're not really sure. We can't necessarily predict. The last trend was metallic character. We looked at that today. And it goes from, it gets bigger towards in the direction of the arrows. Okay. So if you can make sure that you can, in your mind, process these high points, these major concepts, these major points, then you should be able to work your homework problems as well as perform well on this particular part of the exam. The other thing that we have to remember is that our other periodic trend tells us that we can predict the charges based on the position on the periodic table. So we know we have our alkali metals in period 1. They like to be +1. I know you cannot see that. You know, next to it, you've got your alkaline earth. They like to be +2. Then you've got your halogens way over there that are -7. So just look back at that slide, but basically know what all of these groups, you remember we said that those specific groups had special properties. We call the first one the alkali metals, the second one the alkaline earth. Group 7 we call the halogens, and group 8 we call the noble gases, because they have special properties within those families. I tried to put a problem on here that summarizes every single thing, that gives you an example of just about everything, and just so you can practice. Be honest with yourself and try to make sure you go back and reinforce these concepts first with yourself, and then look at the solutions. Okay, so I'm gonna hand these out. And I think Dr. Montgomery should be here. Well, she's got 10 minutes before she comes. So you can make the whole thing be before she gets here. So she's gonna come and answer questions about mastering chemistry and the homework problems and technology and technical difficulties that you have. So the periodic table, from top to bottom, the number of the period you got from. So as soon as you get this, start the problem like 1, 2, 3, 4, 5, instead of down to the bottom. This is what you can do that. You always get to use that. It's just real time, not to be turned in when you kind of get it for questions, and you'll be very well on your own. I want to get your paper. I don't want you to pass this, do I? So why don't you guys work together right now on the first one? And please don't forget that to be successful, you've got to be reading, you got to be studying every day, and you have to be practicing.